In this session, we are going to talk about the basic statistics. So, as a part of the agenda, we will initially cover what do we mean by averages, what are the different kinds of averages. I think to some extent you would be comfortable with the terms like mean, median, mode. How do I really attribute these kind of computation of averages with discrete random variables as well as with continuous random variables, right? How do I really find different kinds of averages for discrete as well as continuous? Then on the same line, just a small extension, what do we mean by expectations and expected values? How are they really linked with the concept of averages? So we'll try to discuss that aspect as well. And once we are done with the averages, we will get into the understanding of the variance and the standard deviation of a set of data. And on the same lines, we'll extend it to the situation called standardized variables. What do we really mean that a variable is standardized? How am I really converting a regular variable into a standardized variable? What do I mean by that? And then moving on to two variable scenarios where we will be talking about the covariance as well as correlation. What are they? What are the definitions of them? And what is the kind of relationship that is existing between them? And the application of this covariance correlation to the concept of portfolio variance. So we'll try to bring in the concept of portfolio variance. How can it be computed by the understanding of the above definitions? And from there we will move towards understanding of the different other moments of the distribution apart from mean and variance. First of all, what do we mean by moments? And what are the other kinds of moments that are associated with the distribution of a data, especially talking about the words like skewness and kurtosis? What do we mean by them? How do we measure them? So all that comes into this particular topic. And finally, we will also try to bring in the concept of co-skewness and co-kurtosis, just like covariance, correlation. We will also bring in the co-skewness and co-kurtosis as a concept. So these are the different things that we will look at as a part of this particular chapter. So let's get started. First of all, whenever we are talking about the statistics, we are talking about a collection of data and trying to interpret that collection of data, right? So going with that interpretations, initially we are starting with the term called averages. So we use averages in some form or the other for different purposes. But just to classify them on a broad scale, we have three major definitions of averages which we all know in some form or the other: mean, the median, and the mode. These are the three different definitions of average. And out of them, though all three of them are used, mean is one of the most popularly used measure of average in case of risk management. Now, whenever we are talking about the word average, we know the mean, we know the definition straightforward. I am doing the summation of the numbers, and that summation I am dividing by the total number or count of the values. So sum of the values divided by the count of the values. If I am talking about the ages of 10 people, I sum up all their ages and divide by the total number of people, which is 10. right? So typically we denote the mean of the population as mu. When I'm talking about the population, I'm trying to find the mean of the entire data. So which I'm calling it as mu, and I'm trying to find the summation of each and every observation for all the n observations. And after I summed it up, I'm dividing it by the number of observations, which will give me the mean. Now, whenever in the statistical world, we have to clearly distinguish between the word population and the word sample. Population is when I'm taking the entire data, whereas sample is when it is only forming a subset of the entire data. So generally the term mu stands for population mean, whereas the term x bar stands for the sample mean. Even there I am adding up 1 to n, but n is not the total number. Probably the total possible values could be much more than n. So n is only a sample of that entire data. Then I call this x bar as the sample mean. So generally, absolute certainty, absolute mean is very rare in many fields, especially in the world of finance and risk management. This mu is very a rare situation. So which means this will not be available in reality. I have to generally estimate the stuff. Especially, let's say I'm talking about the mean return of a stock. I don't have the value for the mean return. I'll take a sample of data from the historical, compute the mean of it, and based on that, I try to estimate what could be the mean for the next period. So, which means when I'm using a sample of data, underlying the mean of it, using that as a mechanism for estimating for the future period. So in this whole thing, there is an assumption. Some process is actually generating the data, right? Some process is actually generating the data, and the properties of that particular process are constant over time. The statistical properties of that particular process are more or less constant over time. And that is where we are talking about uh, for this particular process, there is something called a true mean, which we can't observe directly from the data, and we have to estimate it from the sample. So that is where the sampling and deriving things from the sample makes a very important aspect. So when it comes to the mean, sample mean and population mean, the definitions are more or less one and the same, but the only difference lies in case of a sample, I'm not taking the entire data set. So I generally get the sample mean with x bar. And to a large extent, what we say is the sample mean is a much better estimate for the population mean. Population mean or the true mean of the population. Sample mean, we find out and use that as a better estimate of the population mean. Based on the sample of n data points, we try to compute the sample mean, and we say that that is a better estimate of the population mean, right? So that's how we get into the mean. Similarly, median as well as mode, they are also different forms of averages. So again, usage wise, they don't have too many applications in finance like the mean. But median is typically, we know that whenever we are arranging the data in an ascending order or a descending order, that particular value which is in the center, it divides the data into two halves. So half of the data is below the median value, the remaining half of the data will be above the median value. So that is how we are identifying the median of a particular data set. And coming to the mode, it is that particular data it is that particular observation that occurs with the highest frequency. So if we have some kind of a data set, we can compute all these things, right? Let's say I'm having some kind of a data set, let's say the returns. If I'm talking about the returns like -20, -10, -5, -5, 0, 10%, 10%, 10%, and 19%. Now, first thing, median. Okay, all these are already arranged in the ascending order. So I can pick up the middle value. So 0% is my median. So which is the value that is coming maximum number of times? This is coming 2 times, whereas this is coming 3 times. So 10% is my mode in this data. So these two are easily observable and easily computable. But when it comes to the mean, I have to add up all of them: -30, -35, -40, plus 30. -40 plus 30 minus 10 plus 19. 9% is the total. Divide by the number of values, which is 9. So mean is coming out to 1%. So I have a scenario where mean is 1%, median is 0%, and mode is close to 10%. So these are the different calculations that we are doing on a sample of data. A few important points when it comes to the median. If there are odd number of observations like 9 here, then the middle value is the median. In general, it is n plus 1 by 2th element that forms the median. Right? So if there are 9 elements, 5th element is the median. If there are 10 elements, let's say I am putting another -20 here. So then 5.5th element is the median. So I'll take the 5th. This is my 5th. This is my 6th. So 5.5 is somewhere in between the two. So I take the average or mean of these two, saying -2.5% is my median here. Right? So that's how we compute the median. So I'm taking the average of the two centermost points in case there are even number of observations in the data. So median also I'm using for summarizing the data, and especially when the data is more and more asymmetrical, where I'm seeing too many outliers in the data, too many extreme values in the data, either on the much lower side or on the much higher side, some abnormal values are observed, then typically mean is very heavily biased because it adds that number and it gets very heavily influenced because of the outlier value. Whereas the median does not get influenced that way. And that's one of the prime reasons median will be used for summarizing the data, which is more and more asymmetrical in nature and which has significant outliers in it. Right? Now, coming to the mode, in general, a data set can have more than one mode, where multimodal, or it need not have any kind of a mode, which is like a no model kind of stuff. So because of this reason, mode is more and more rarely used, right? Because in some cases it might be possible that the maximum frequency is shared by two or more values. Then it becomes multimodal, and none of them are repeated. Then it becomes no model kind of stuff, right? So that's how the mode goes, and that's the reason mode does not have too many usages in the world of finance and risk management. Typically, when we have computed the mean, each observation is counted only once and exactly, which means each observation was actually given a very equal weight. But in reality, each one can have a different weight. Some of the observations I can give more weight, some of them I can give lesser weight. Right? Especially I may want to give for large, if I'm taking the returns data of the companies. For large companies, I want to give more weight. For small companies, I want to give lesser weight. Probably based on their market capitalization, I want to give the weightage to that particular company. Or if I am taking the daily returns and for computing the average, I don't want to give equal weightage to all the days. I want to give more weightage to the recent data and a very less weightage to the older data. So in all these cases, we are typically computing what is called as the weighted mean. We are taking the mean, but we are not giving equal weight to all observations. See, typically, if you talked about the typical normal mean, what is that we are saying? This is the formula. So, which means A1, if you expand it, it is A1 by N plus A2 by N plus so on AN by N. So, every observation is multiplied by 1 by N only, which means the weightage is purely 1 by N equal for all of them. Whereas in a weighted mean, I'll change these numbers in such a way that the sum of these weightages is 1, but each individual weightage goes with a different kind of a pattern. So when that is what we are calling as a weighted mean. So typically, if I am really interested in finding out the weighted mean, it's as good as I am multiplying each observation with its corresponding weight and then adding all of them, dividing the denominator with the sum of all the weights. So this is what will give me my weighted mean. And the special case is if all the weights are exactly the same, then the weighted mean will become the standard mean. Correct? All right. The next thing that we will move forward is, okay, extend this concept of averages to both discrete random variables as well as to the continuous random variable. I have to compute the mean, median, mode, let's say for the discrete random variable. Now, a simple way is for the mean, it is nothing but it's just like your weighted average. The only difference is each observation you multiply with its corresponding probability and then add it up. Because in the denominator, the sum of all the probabilities is always 1, so I can very well ignore it. So it is as good as saying multiply the probability with its corresponding value and sum it up. That is what we are calling as the mean. So it's a special case of the weighted mean where the outcomes are weighted by their probabilities and the sum of all the weights is equal to 1 because the sum of all the probabilities is equal to 1. And coming to the median for a discrete random variable, it is that particular value where the probability that a particular value is less than or equal to the median is exactly 50%. So which is nothing but the cumulative distribution. Right? The probability that a random variable takes a value less than or equal to the median is exactly 50%. So which means the other side is also 50%. So the probability that the x random variable takes a value greater than or equal to the median is same as the probability that x takes a value less than or equal to the median, and both of them should be exactly equal to the 50%. That is how we can compute the median. And then coming to the mode, that particular value which is associated with the highest probability, where the probability, the frequency is the highest. So here the frequency is replaced with probability. So which has the highest probability, then that is what we are calling as a mode. And we know that the mode need not be unique. There can be a multi-model kind of a scenario also. So let's take one simple example to understand these three for a discrete random variable. So let me say that there are two bonds. I'll take an example where there are two bonds. The worth of each bond is $100. And let's say for each of these bonds, if each of them default, so the bond one defaults, the worth will become $20 at the end of the year. If bond 2 defaults, the worth will become $20 at the end of the year. Right now the worth is 100, but if it defaults, its worth will become $20, each one of them. But if they don't default, they are still worth $100 at the end of the year. Now, the probability that both the bonds default, right? B1 and B2, both of them default, is 20%. The probability that neither bond defaults, so B1 bar, B2 bar, neither of them defaulting, is 45%. So there is a remaining chance, 35% chance that one of them can default. So these are the different possibilities. There is a 20% chance that both of them will default, 45% chance that none of them will default, and 35% chance that one of them will default. Now for this, I want to find out the mean, median, and mode at the end of the period. Okay, if both of them default, the worth is 40 bucks. If none of them default, the worth is 200 bucks. And if one of them default, the worth is 120, because one of them will become 20, the other one will be 100. So if one of them default, the worth is 120. Now from here, I can very well find out the mean. So the mean is probability is multiplied by the value. 20% into 40, which is 8. 45% into 20, 200, which is 90, plus 35% times 12, 120. So which is around 42. So this is working out to 140. So the mean is around 140 for this case. And okay, when I come to the mode, the one that is having the highest frequency or the highest probability. So the mode is 200, the most likely single outcome. And when it comes to the median, I'm looking at that particular, so here it is 40, 120, 200. So I'm arranging it in the ascending order. Now less than or equal to 40 is 20%, but less than or equal to 120 is 55%, 20 and 35. So 120 is that particular number that will divide the whole data into two halves. So 50% of the data will be below 120 and 50 less than or equal to 120. 50% of the data will be greater than or equal to 120. So 120 will become my median for this example. Right? So that's how we compute the mean, median, and mode for a discrete random variable. Then let's extend this concept to a continuous random variable. So we can very well find the mean, median, and mode for a continuous random variable also. And if I want to find out the mean, simple. I take the minimum and the maximum as it is. See, if I'm doing it between the minimum and the maximum, if I'm integrating f of x dx, then I'm going to get 1. But if I multiply it with x, means value multiplied by its corresponding probability. That is what was the mean. So we are doing the same, integrating the product of the variable and its corresponding probability density function. So it's as good as calculating the mean of a discrete random variable also. Multiply the variable value with its corresponding probability. So if I do this, I'm going to get the mean of the continuous random variable. When I'm talking about the median, it's as good as saying, so the minimum value, if I'm doing the integration between the minimum value and the median, the f of x dx, I'm integrating f of x between the minimum and the median, this should be 0.5. And similarly, if I am integrating it from the median, between the median and the maximum value also, the area under this probability density function should be equal to 0.5. So the 50% probability that the values less than or equal to the median, less than or equal to the median is 50%, greater than or equal to the median is also 50%. So this is the way we can end up computing the median of our particular distribution. So it's as good as saying, because I'm going from the minimum value, I can very well say that the cumulative distribution function m should be equal to 0.5. So I can very well express it even in this form. If I have a cumulative distribution function for that particular value of m, where the cumulative distribution function value is zero point 0.5, that forms my median. Then coming to the mode, it is the maximum of the density function. So I'll find out the maximum value of the density function, and that is what I'm calling as the mode, and in general it need not be unique. There could be multiple modes again. So we'll take the example. If I'm taking let's say f of x equal to x by 50, where 0 less than or equal to x less than or equal to 10. Let's say for this data I want to find out the mean, median, mode. So first let's get into the mean. So I have to really integrate between the minimum and the maximum. So minimum and the maximum is 0 to 10 f of x dx, but x into f of x dx. So this is working out as 0 to 10. I'll take the 1 by 50 out, x squared dx. I know for x squared, it is x cubed by 3, the integral value, integrated between 10 and 0. 1 by 50 times 10 cubed by 3, 1000 by 3, which is working out as 1000 by 150. So that is what is working out as the mean of the data. 1000 by 150, which is 100 by 15, which works out to 6.67. 6.67 works out as the mean of this particular data. So we are clear on finding out the mean. Now we'll look at the median. Integrating it between 0 and median, f of x dx, x by 50 dx should be equal to 0.5. So 1 by 50 times x integral is x squared by 2. This I am integrating it between the median and 0, which should come to 0.5. So which is nothing but median squared by 100 is equal to 0.5. And from here it works out that the median squared is 50, which is median is square root of 50. So just around 7 will be my median for this particular data. And when I'm looking at the mode, the one that is having the highest frequency, right, the one that is having the highest probability, so maximum of the PDF, I know that the maximum value of the PDF is coming out to be 10, so the mode will come out to be the 10 in this case. So all the three things, so the PDF is having a maximum value. I know the maximum value here comes when x is 10. So the PDF is having a maximum value at 10, which means the mode is 10. So all three we were able to compute the mean, median and mode for a continuous random variable. So we can do this process both for discrete as well as continuous random variables. All right. Now let's move on to the next aspect, which is expectations. Probably there is a lot of similarity between the world of expectations and averages, and they are used interchangeably also. And when we are talking about the expectations, we are looking at kind of forward looking. right? The major difference between the averages and expectations is the forward looking part. Generally, when we talk about the expected value of x, it is nothing but I'm taking the probability of x1 occurring multiplied by x1 plus probability of x2 occurring multiplied by x2 and so on, which is nothing but I'm also doing there also I'm doing the same probability of xi multiplied by xi, and I'm summing it over 1 to n. So the concept is more or less the same, the calculation is more or less the same. The mean and the expected value generally will have the same numerical value, and this will exist both for discrete as well as continuous variables also. For any random variable, we see that the expected value is same as that of the mean. But one thing we have to understand is the major difference between the two exists in averages is generally based on, or the mean is generally based on the historical data, whereas the expected value is more of a forward looking. So that is where the difference lies. If we assume that the historical data is generated by some process and that process is going to remain the same in future, then that kind of a strong assumption that we are creating, in that scenario the expected value is same as that of the mean. So there are two assumptions where I can equate the expected value to the mean. One, the historical data, it during a particular period which we have considered, it is generated by some process, and that process continues to be the same even for the future data as well. That is when I can say that the expected value is same as that of the mean. So if my historical mean returns was 15%, and if I assume that more or less similar kind of a process is going to be present in the future as well, then in the future also I can take it as 15%. Then the historical mean will be the same as the expected value. But if the future is going to be different from the past, then this expected value need not be the same as that of the mean. But in general, in many financial applications and in the world of risk management, we generally assume that whatever the data that has generated the past, whatever the process that has generated the historical data, that process is going to be more and more consistent and more constant even in the future. So that's a major assumption that we make in the financial and risk management world. So in case we are challenging that kind of an assumption, then that is where the difference between the expected values as well as the mean is going to come up, right? So we have lots and lots of these kind of assumption based applications. As we move further, we'll see we'll use this similar assumption in regression. We'll use similar kind of assumption in time series. So there are different areas where we use similar kind of assumption, right? Now, just let's take one small example, right? I'll continue the bond example itself. Let's say I am talking about uh, a bond, right? It is having a notional value of $100. So, as far as your understanding is concerned, there is a 20% chance that the bond will default, and if it defaults, its worth at the end of the year is going to be $40. But there is a 30% chance that it will be downgraded. Credit worthiness will go down. In that case, it is not defaulting, it's only downgraded. In that case, the worth of the bond is going to be $90, which means the remaining 50% chance that the bond will not default or not get downgraded, and in that case, it's going to be $100. Now, I really need to find out, let's say using an interest rate of 5%, I need to find the price of the bond. So for that, first thing I need to know is what is the expected value at the end of 1 year. So I'll use the same probabilities multiplied by the values. 20% of 40 is 8, 30% of 90 is 27, and 50% of 100 is 50. So it is 85. So my expected value at the end of the year is going to be 85, which means the present value of the bond is 85 to the power of 5% times T is 1. 85 divided by e to the power of 0.05 will give me the worth of my bond. So here is where we are using the concept of expected value. I am expecting that 20% chance that the bond is going to default. Now, whatever could be the reason behind that expectation, whatever could be the cause of the expectation, we are not bothered. If it is purely based on the historical value and that same process is going to repeat in the future, then that is where the mean would be the same as the expected value. Right? Now, let's talk about some of the properties associated with the expected value, something which can really help us in doing a lot of numericals. One, the expected value operator is more and more linear. What do I mean by that? Expected value of x plus y is same as the expected value of x plus expected value of y. And if I am interested in finding out the expected value of some constant times a variable, it is same as constant times the expected value of x. And here is one more. It's not multiplicative. Additive is fine, but it is definitely not multiplicative. There are some cases where it is. We'll look at them, which means expected value of xy is not the same as expected value of x times expected value of y. Only in some specific cases we will find that, and the typical case where we will find is when x and y are independent. Right? We'll see that later. But when x and y are independent events altogether, we'll see that expected value of xy is same as the expected value of y. But in other cases, this relationship will not hold true, whereas the additive relationship is holding true, which means the same logic, expected value of x squared is not the same as expected value of x whole square. And later we will also try to understand probably the difference between these two values is nothing but the variance. We'll see slightly later. Expected value of x squared minus expected value of x whole squared is nothing but the variance itself. So which means these two are not going to be the same at all. So that's one thing we have to keep in mind. That's one formula that we really need to be comfortable with. Some relationships associated with the expected values. Right? Now let's look at a simple example to just try understanding the expected value concept. Let's say I'm taking y is x plus 5 cube plus x squared plus 10x. And I need to find out the expected value of y. So somewhere some information is given for me. Expected value of x is 4. Let's say expected value of x squared is 9. And expected value of x cube is 12. So here it is very clear that the expected value of x squared is not the same as expected value of x whole squared. Expected value of x cube is not the same as expected value of x whole cube. So here we are expanding it. So this is the expected value of, I'm expanding this, x cube plus 3x squared into 5. 15x squared plus 3x into 5 squared. 75x plus 125 plus x squared plus 10x. So this entire thing is becoming expected value of x cube plus 16x squared plus 85x plus 125. Now, so because it is additive, I'll make it separate. Expected value of x cube plus 16 times expected value of x squared plus 85 times expected value of x plus expected value of a constant is always a constant. So expected value of x cube is 12 plus 16 times expected value of x squared is 9 plus 85 times expected value of x is 4 plus 125. So which is nothing but 12 plus 144 plus 340 plus 125. So whatever is it, that is coming out to be the expected value of y. So that's the way we are simplifying the stuff. Fine. Now we'll move to the next topic where we are trying to understand the variance as well as standard deviation. We always deal with these two things together because we know that standard deviation is nothing but the square root of variance. So if I know the one, the other is quite simpler to find out. So whenever we are defining the word variance for any random variable, so we are talking about the level of unpredictability, the level of randomness that is associated with our variable, the level of unpredictability that is associated with our variable. And as a definition or as a notation, we denote it as sigma squared, and it is nothing but the expected value of each observation of the variable or the random variable, each value minus the mean square. Expected value of x minus mu squared. So expected value of the difference between the variable and the mean squared. That is what we are calling as the variance of the random variable, and the standard deviation simply denoted by sigma, which is just the square root of the variance. So we'll always compute the variance, and from there we are computing the square root. Obviously we are taking only the positive term. And in general, in the finance world, this standard deviation is what is typically called as volatility. Right? So just like the way we are calling mean and average as interchangeably used, the same logic goes with volatility and standard deviation. Standard deviation is more of a mathematical concept, whereas volatility is more of a finance concept. So if I'm simply saying there is a 50% chance when I'm doing some investment, there is a 50% chance that I'll gain either 10 bucks and 50% chance that I'll lose 10 bucks. Then I really want to find out what is the variance or the standard deviation. So for that, first of all, I am finding out the expected value, which is the mu, which is going to be 50% times 10, which is 5, 50% times minus 10, minus 5. So the mean is 0. Now for the variance, I am finding out expected value of x minus mu squared. So there is, okay, this is x, this is mu. So the probability multiplied by 10 minus 0 squared plus the remaining probability multiplied by minus 10 minus 0 squared. So 0.5 times 100 plus 0.5 times 100, which is working out to 100. So my variance is going to be 10, and from there my standard 100, and if I say standard deviation is going to be the square root of that, which is going to be 10. So this is the variance and the standard deviation, especially when I'm computing it for the entire population where all the possible outcomes are known. Whereas if so, the typical way we are computing the standard deviation or the variance is each observation, subtract the mean, square it, add it, and I divide it by n. That is what will give me the typical variance. That is what is the expected value meaning. Whereas if I have to go with the sample variance, a small difference exists. There is no difference in the calculation for a sample mean and a population mean. Whereas for variance, we have a small difference. Everything remains the same. Observations minus the mean squared, summation, but we divide it by n minus 1, not n. The sample variance, we get it by dividing by n minus 1 rather than n. Probably when we talk about the unbiased estimators, we will come to know later that this formula is a very much unbiased estimator for the population variance compared to dividing it by 1 by n. That's the reason we use n minus 1 as a mechanism for the dividing the summation of the squared deviations from the mean. So we have computed the sample mean and divided by n minus 1 and not the n. So if the mean is known, now simple way for you to remember, if the mean is known, population mean if it is known, or we are computing the population variance itself, then we divide by n. But if the mean is not known, wherein we are estimating the mean from the sample itself, then the better estimate for the variance is dividing it by n minus 1 and not n. So that's the thing that you can remember for the time being. Now, so we know that this is the typical definition of variance. So let's try to derive something. My variance is nothing but expected value of x minus mu squared. Now let's expand it. Expected value of x squared minus 2 mu x plus mu squared. Okay. So now because it is additive linear, so I'll split it. Expected value of x squared, because minus 2 mu is constant, I'll take it out, say expected value of x plus expected value of mu squared is a constant, I'll take it as mu squared. So this becomes expected value of x squared minus 2 mu times expected value of x is nothing but mu plus mu squared. So overall is coming out as expected value of x squared minus mu squared. Mu is nothing but expected value of x. So typically I can write it as expected value of x squared minus expected value of x whole square. So this is the what is the definition of the variance. So these two definitely are not equal, and if they are equal, it means that the variance is 0. So there is no variance, there is no standard deviation. So you can either remember this formula for variance, or even you can remember this kind of a formula. So depending on which of the tools, see typically when we are using a computer program, I can very well prefer this, because in this case first I have to compute the mean and after that compute the variance. Whereas here both are based on the x only. So I can directly compute both of them. So that's the reason for computer programs I prefer this. So depending on the usage, we can use any one of them. Right? So based on the numbers, we can really find out the mean, the variance of a particular random variable. And in general, it is assumed for a lot of calculations in the world of finance, especially for short duration returns, short term returns, daily returns, etc. For very short duration stuff, we make an assumption that the mean returns is approximately zero. If the mean return is zero, then probably this part is becoming zero. So variance is nothing but the expected value of the squared return. So that's another, so it's nothing but the mean of the squared returns is what we are calling as variance, especially when the mean is becoming closer to zero. Now, the same logic, if I have to compute the variance for a continuous variable, yes, just like the way we have done in case of mean, minimum and the maximum, f of x dx, but this I have to multiply it with x minus mu square, because the value multiplied by the probability density function. So this is what is giving me the computation of a variance in case of a continuous random variable. Now, a few important points we really need to understand regarding the variance. If I want to talk about the standard deviation for a constant multiplied by x is nothing but constant times the standard deviation of x. But if I want to find out the standard deviation of a constant added to x, it will be the same as standard deviation of x itself. Adding a constant will not change the standard deviation, but multiplying with the constant will increase the standard deviation by the same amount of value. Right? So a couple of important points that we really be using at a later point as a part of our different computations. So we really need to be comfortable with this concept as well. Then the next topic that I'm going to deal with here is the topic of standardized variables. See, many a times the different variables that I use, they have a different mean and they have a different variance or standard deviation. But when I convert that particular variable into something where mean is 0 and the standard deviation is 1, any variable, I convert it in such a way that its mean is 0 and standard deviation is 1, I call those kind of variables as standardized variables. And how do I really do that? For every observation, I subtract the mean of it and the resulting value I divide it by the standard deviation of that particular data. We are creating a new random variable whose mean is 0 and whose standard deviation is 1. So for expected value of y, if for x I subtract the mean and divide by the standard deviation, I get the expected value of y is 0 and I get the standard deviation of y is 1. So that is what we call as the standardized variable. So x is standardized in this case, or simply I call y is a standard random variable. And I can very well, so which means what is the simple way for me? When I am starting with x, find the mean of x, find the standard deviation of x. From each observation, subtract the mean and then divide by the standard deviation. That is the standardization process. And in some cases, we also require the inverse standardization process, which means if I am getting a standardized value, I multiply that with the standard deviation and after that add up the mean to get the actual observation, right? So that is what we are calling as the inverse standardization, which have a lot of applications. So definition wise, we really need to be comfortable in terms of understanding it. Now, let's assume that there is a variable y, just taking it as an example. I'm taking a random variable y where the expected value is 0 and the standard deviation of y is 1, which means y is a standard random variable. And now I'm having two other variables, let's say x1, which is sigma y plus mu, where sigma and mu are constant. Then I'm also having x2, which is sigma times y plus mu. Now I really want to find out the expected value of x1. Okay, let's try. What is the expected value of x1? Sigma times expected value of y plus mu. So what is the expected value of y? It is 0. So this is coming out as mu. Whereas if I want expected value of x2, it is nothing but expected value of sigma y plus expected value of sigma mu. And I can very well find out sigma times expected value of y is 0 plus this as a constant, so it becomes sigma mu. So typically, depending on the expected value of x and the expected value of y, I can very well transform it into some other variable, standardized or non-standardized kind of stuff. So from a standardized, I can make it non-standardized, and from the non-standardized, I can make it standardized. So that's one more important aspect, standardization of the variables, where we have a lot of applications in the world of finance and risk management. All right. Now, let's move on to the next topic, which is where we'll try to understand covariance and correlation, the relationship between them. So till now, whatever the statistics that we have computed, they are primarily targeted towards one variable. Whatever the mean that we have computed, variance, standard deviation, everything was based on one variable. Whereas in the world of risk management, we are primarily interested in looking at the relationships between two or more variables. Right? I am more interested in looking at the relationship between the stock returns and the index return. So this is where we need to bring in two variables at a time. And if I'm trying to understand the variance with respect to two variables at a time, that is what we are calling as the covariance. So I'm not looking at the deviation from the mean of one variable. Here I'm looking at the relationship between the deviation from the mean of two variables. I take two variables at a time, see how the deviation from the mean for each of these two variables is changing. That is what I call as covariance, generally represented as sigma xy, where I'm looking at the expected value of x minus the mean of x times y minus the mean of y. So I'm seeing whether this is positive or negative or very much closer to 0. So this is how we look at the covariance. So which means if x is same as y, then we are getting nothing but the variance only, because I'll write it as x minus mu of x, which is nothing but x minus mu of x whole square. So when x and y are the same, covariance is nothing but the variance. So the variance is nothing but the covariance of the variable with itself. So it can so happen that this could be positive, this could also be positive. In that case, the covariance could be positive. This could be negative, this could be negative, still the covariance could be positive. But this is positive, this is negative, or this is negative, this is positive. My overall covariance could either be positive or negative, depending on which one is higher compared to the other one. So whenever x is tending to move above mu x and y is also going above mu y, So where the deviations of both of them are positive, or where the deviations of both of them are negative, I can look at the covariance to be more and more positive. But if it is the other way, I can very well look at the covariance to be negative also. And if more or less equal number of ups and downs, so sometimes this is up, sometimes this is down, and sometimes when this is down, this is up. So the expected value will be around 0. In that case, I can't come out with any kind of solid relationship existing between the deviations from the mean. So if we look at, okay, sigma xy, expected value of x minus mu of x times y minus mu of y. Let's do some basic calculations on it. Multiply xy minus mu y times x minus mu x times y plus mu x mu y. Good. Now I'll pull the additive part. Expected value of xy minus mu y times expected value of x is nothing but mu x minus mu x times expected value of y is mu y plus mu x mu y. So I can take it out and finally say expected value of xy minus expected value of x times expected value of y. So this is what is the definition of the covariance. So when the covariance is 0, then we see that the expected value of xy is same as expected value of x into expected value of y. If you remember when we have discussed some of the relations relating to the expectations, we said that these two are equal only when the variables x and y are independent. So when x and y are independent, I can very well say that the covariance between them is very much 0. So if the covariance between the two is 0, then I can see the multiplication relationship that is getting maintained. And one more important point regarding the covariance is just like the variance, if I am doing for a population, right? If I am doing for a population, I'll look at it as x minus mu times y minus mu y, sum it and divide by n. Whereas when I'm looking at for a sample, it will still be the division by n minus 1 itself. So that's one more point that we really need to be remembering. Then, going forward towards correlation, just a related concept. See, in case of covariance, I may get a value of plus 20, minus 100. I don't know whether this is high or low, because covariance is very much based on the units. So if I had taken the data in meters, I would have got a different covariance, and if I have taken the same data in kilometers, I would have got a different covariance. So I can't clearly say whether based on the covariance, whether my number is higher or lower. So that is the reason we have introduced the concept of correlation. Correlation is nothing but the covariance. I'm taking their covariance and I'm dividing it by the product of their individual standard deviations. So the numerator is covariance and the denominator is the product of their respective individual standard deviation. And what we really observe is this value always lies between -1 and +1 only. That's very important, interesting property of the correlation. We see that the value will lie between -1 and +1. If it is very much having +1, we say it is a perfectly positively correlated. And even if it is -1, we say it is perfectly negatively correlated. So anything on the extremes, we say that the correlation is much stronger whereas somewhere in the middle, the correlation is becoming weaker and weaker. And in many cases, when we are seeing that the correlation is very high, we will be tempted to some extent trying to understand a causation relationship. Can variable 1 cause the value of the variable 2? Though in reality that need not be the case, but to some extent it gives us some kind of a pointer. There is a possibility that the variable 1 can imply variable 2. So generally we find that if they have the same underlying factor which can contribute to their growth, even in those cases we see that the correlation is going to be much higher. But of course, the reality is correlation never means causation, but just a pointer for us to really look at. And in case two variables are uncorrelated, right? I see that if the two variables are uncorrelated, we'll see that the correlation coefficient is 0. But if the correlation coefficient is 0, it doesn't mean that they are unrelated, because correlation typically measures the level of linear relationship between the variables. And it might very well be possible that these two variables might be sharing some other form of a relationship, like a quadratic relationship. If I see that y equal to x squared kind of a relationship, then if x is -1, 0, 1, y is 1, 0, 1. If I try finding out the correlation between these two pairs of data, I see it is 0. So it is from my correlation, I will be able to say that there is no relationship between these two variables. But the reality is not that. They are very strongly related by the relation of y equal to x squared. So what does that mean for us here? The simple thing that we can make out here is correlation only talks about the degree of linear relationship that is existing between the variables. It does not consider the presence of the non-linear relationship between the variables. Then, how do we apply all these concepts to the world of portfolio variance? All these concepts go into the world of portfolio variance in finance, where I'm looking at a portfolio of securities, two or more securities. I need the underlying volatilities of each one of them, and along with that I also require the correlation between the X and Y kind of securities. So the interesting thing, let me talk about two securities A and B. I'm not going into the proofs and all. Let's say their means are mu A and mu B, and let's say their standard deviation are sigma A and sigma B, right? And so these are following kind of random variables xa and xb. Now if I want to know the variance of a portfolio, it is nothing but the variance of A plus variance of B plus twice the covariance between A and B, which is nothing but, now we know covariance, correlation of A and B is same as covariance between A and B divided by the standard deviation of A into standard deviation of B. So which is nothing but, now I can find the covariance of B as a multiplication, which is correlation between A and B times standard deviation of A times standard deviation of B. This is what we get as the formula for the variance of the portfolio, where rho AB is the correlation between the XA and XB, right? So you could see that this is more or less a frozen stuff. This is more or less a frozen stuff. These two are frozen stuff which are associated with that individual security. But this is something which is talking about the relationship between the two. So if it is -1, probably my overall variance is coming down. And if it is +1, it looks like the overall variance is actually going up. Right? So if the correlation between A and B is positive, the overall variance is higher compared to when the correlation is negative. Now, some interesting things let's bring in. Now, I'll use this expression sigma A squared plus sigma B squared plus 2 correlation sigma A sigma B. Now, let me assume that the variances or volatilities of all the securities are the same. Both the securities is same. Then, what is the variance of the portfolio now? Sigma A, wherever sigma B is there, I'll substitute it with sigma A only. So, 2 times correlation between A and B, sigma A, sigma A. So, 2 sigma A squared plus 2 correlation AB sigma A square. So I can very well take 2 sigma A squared times 1 plus the correlation between A and B. Now we know that the correlation between A and B can be anywhere between -1 to +1. So if I assume that it is -1, then the variance of the portfolio is 0. If the correlation of the portfolio is between A and B is +1, then the variance of the portfolio is 4 sigma A square. And the standard deviation is the square root of that, which is the double of sigma A. So we are seeing that the variance will lie between 0 and 4 times the variance of the security of each individual security, and the standard deviation lies between 0 and twice the standard deviation of the individual security. So the same logic, now we can take it further, right? Or probably if the correlation between them is 0, then it is the variance of the portfolio is nothing but 2 sigma A squared, and standard deviation will come out as sigma A times square root of 2. So these are some of the important relationships that we are able to see, and we can very well extend this very comfortably for n number of securities also, wherein I can very well look at if there are n such kind of securities where the variance is more or less equal, I get the variance of the portfolio is each individual standard deviation times square root of n, especially if the correlation between them is 0. This value is applicable only when the correlation between them is 0. And this is what we actually use in a lot of places. When two variables are unrelated, when n variables are unrelated, means the correlation between them is more or less 0 and have equal variance, then the variance of the portfolio is nothing but the individual variance, which was that equal variance times square root of n. And this is what we call as square root rule. So for the addition of uncorrelated variables, this square root rule can very well be utilized. And what we really observe is in the world of finance, we take so many random variables which we classify them as independent and have similar statistical properties, which are otherwise called as IIDs, independent identically distributed kind of variables. So their statistical distribution is more or less identical and they are independent. Whenever we are coming across these kind of IIDs, so which means their variance is more or less the same, and if I am really, and the correlation between them is 0, In that case, if I want to find out the variance of the portfolio, I can very well take it as sigma times square root of n. We use this very heavily in the world of risk management as well, and in the time series context also, we keep using the concept of independent and identically distributed variables. So, simply put, whenever we are talking about the variance of the portfolio, we will be using both the variance of the individual securities as well as the covariance and then the correlation between the securities as well. Now, using the same context, let's say I am more interested in finding out the variance of some linear combination of the variables. So let's say I'm talking about y is some a times xa plus b times xb. Then also, if I'm interested in finding the variance of y, I'll simply do it as a squared times the variance of a plus b squared times the variance of b plus 2ab times correlation between a and b, standard deviation of a, standard deviation of b. So this kind of a concept will always go ahead whether I am doing whatever is the linear combination of the variables. And this concept will actually help me in terms of doing the hedging as well, which we'll try to cover at some other point in time, or probably let's quickly look at how this can help me in hedging. Let's say I'll take a simple example. I have a security A which I have $1 and I want to hedge it. I want to mitigate the risk of it using security B, and I am interested in buying some H dollars of security B. So my net value of the portfolio, if you look at, it is $1 of XA and it is H dollars of XB. This is what is the worth of my portfolio. Now, based on this, I can find out what is the variance of my portfolio. I want to minimize this variance, remember. So, it is nothing but XA squared plus H squared, the variance of B squared. This is variance of A squared. H squared variance of B squared plus 2H times, going with that same formula, correlation existing between A and B, standard deviation of A times standard deviation of B. This is what is the variance of my portfolio. And if I'm talking about the hedging, my hedge ratio, my that particular value of hedge where the portfolio will have the least possible variance. So this value should be the least, which means I am differentiating this particular variance with respect to h. If I am and equate it to 0. So which comes out as sigma b squared times 2h plus 2 correlation AB sigma A sigma B. This is my first derivative. I'm equating it to 0. So basically I'm taking out the 2 out. I can take out one sigma B out. So it's coming out like sigma B plus correlation between A and B times sigma A equal to 0. H times H here. So from here I can say H is nothing but minus correlation between A and B sigma A divided by sigma B. So my edge ratio, which is more and more optimal for me, is I can look at the correlation between the two securities, standard deviation of security A divided by the standard deviation of security B. And that is what will give me the edge ratio, which is more and more optimal, which can reduce the variance of my portfolio quite drastically. So that's the kind of usage where we can literally use the concepts of variance, standard deviation, covariance, correlation. So as we move along, we'll try to understand a few more interesting aspects where all these concepts of statistics are very heavily used in the world of finance and risk management. All right. Now, let's move on to our next topic, which we call as the movements of the distribution. So, if we look at the mean, we have called it expected value of x. So this I will generalize it, saying some mk is nothing but expected value of x power k. So when k equal to 1, which is what we are calling as the mean. So this kind of a definition is what is called as a kth movement. Expected value of x power k is what we are calling as the kth movement for a particular random variable x. Right? The mean is nothing but the first movement. Similarly, the other way, we have another representation called mu k, where I am looking at expected value of x minus mu to the power k. This is called as the kth central moment. Means I am trying to find the moment with respect to the mean. So that is what we are calling as the kth central moment. When I say k equal to 2, it is nothing but it's the variance. So we can call variance as the second central moment or second moment above the mean, whereas the mean is called as the first moment. It's not central moment, it's the first moment. First moment of x is the mean and the second central moment of x is the variance. So generally central moments are denoted by mu k and the regular moments are denoted by mk. Right? And generally we also get into the third moment and the fourth moment, but not beyond that. There are hardly any users of the values which are beyond the third moment and the fourth moment. Now just getting into that third and the fourth moment is what are the concepts of skewness and kurtosis. So initially let me talk about the skewness, and after that we move about finding out the kurtosis as well. See, when we are talking about the second central moment, x minus mu squared, this is what we called as a variance. Variance, it is telling about what is the kind of a spread a particular random variable is having around the mean. The same logic, if I am doing the cube of it instead of the square, this talks about the symmetric. How symmetric is the distribution around the mean, right? So this is what is a measure of skewness. But generally what we see is this is the third central moment. Instead of taking it as it is, people generally standardize it. And what is meant by standardization here? They divide this by sigma cube, which is the standard deviation cube. When they divide it by the standard deviation cube, the third central moment divided by the standard deviation cube, this is what is called as the coefficient of skewness. And why we do this kind of a standardization? Because we are removing the units. By doing this, now this is a third degree quantity, this is also a third degree quantity, so the units are simply eliminated, which will really help in terms of comparison. Two random variables can quite comfortably be compared for their relative symmetricity and relative skewness present in those variables. And if I am multiplying the random variable by a constant, still my skewness is not going to change. Right? So that's the reason we always look at skewness as a standardized kind of a variable. And a few important things. if at all a particular random variable is more and more symmetrical about the mean, we see that the skewness value will be close to 0. And if it is more and more positively skewed, I see that the coefficient of skewness will be positive. So sometimes I call positively skewed or right skewed. And if I have a negative skewness or left skewed in my data, then I see that the coefficient of skewness is negative. And typically the graphical representation wise, right, if I am looking at a normal kind of a data, let's say, or symmetric kind of a data, if it is more like this, symmetric on both the sides. But if I am talking about a positively skewed kind of a data, I may see that some kind of skewness comes towards the right. Whereas when I'm looking at a negatively skewed kind of a data, I may see that the values go more towards the left. So that's how I differentiate a positive skew from a negative skew. And it is very, very an important concept when it comes to risk management. There are lots of examples which exhibit positive skewness and negative skewness. So typically when I'm looking at the distributions of two different returns, where more or less they have the similar mean and standard deviation, but if they differ in their skewness levels, two different returns where mean is same, standard deviation is same, but skewness levels are different, I see that investment which is having more negative skewness is going to be more and more risky compared to the other one. So that is where the skewness understanding becomes a very important part. And just like the way we have differentiated the variance, covariance, etc., between the population and the sample, even the skewness computation also differs between the population and the sample. When we are doing it with respect to the population, what is that we are saying? You subtract the mean, cube it, and divide it by the standard deviation. Sum it across and do it by 1 by n. But when I am doing it for a sample, there is a small difference. This part is still the same, xi minus mu by sigma, I do it whole cube. But instead of I sum it up to here there is no issue. But when I have to find out the sample skewness, instead of 1 by n, I'll use it as n divided by n minus 1 into n minus 2. This is what we'll be using. We'll not use 1 by n minus 1 for skewness. Again, this goes with the property of unbiased estimator. This sample skewness is an unbiased estimator for population skewness rather than any other formula. Right? So, whenever we are talking of expected value of x minus mu cube, I can very well find out the expansion also. Expected value of x cube minus 3 mu expected value of x squared plus 3 mu squared expected value of x minus mu cube. So which works out as expected value of x cube, 3 mu times expected value of x squared. 3 mu squared expected value of x is mu. 3 mu cube minus mu cube, which is 2 mu cube. So this is what will come out as the relationship between expected value of x minus mu cube and the individual expected x cube minus expected x squares and expected value of x. So these are some of the differences that we have to bring in terms of our understanding of the skewness, and as a measure, skewness is going to measure the symmetricity of a particular data. right? We can very well, we have derived the formula which is existing between expected value of x minus mu cube for deriving expected value of x minus mu whole cube. And a few important points with respect to the skewness. If the skewness is 0, we said that the data is more or less symmetric. The distribution is more or less symmetric. And when it is symmetric, what we see is the mean, the median, as well as the mode. They are more or less equal. They are very, very close to each other, similar value. But if it is negatively skewed, if a distribution is negatively skewed, we find that the mean is less than the median, which would be less than the mode. And if my data is more positively skewed, I see that the mean is much higher compared to the median, compared to the mode. Though it is not mandatory, but this is a kind of a common relationship that we observe. So as a risk manager, my major problem lies in terms of identifying the impact of the skew on the mean relative to the median. So to what extent the mean is deviating from the median because of the skewness that is present in my data. Very, very important aspect to analyze and appreciate. Right? All right. Then we'll move on to our next aspect where we are trying to understand the kurtosis, which is nothing but the fourth central moment, which is nothing but expected value of x minus mu to the power 4. To a large extent, we see that it is more or less similar to that of the variance, which is the second central moment, which talks about what is the kind of spread that is there in the random variable about the mean. But the only difference is here the extremes are given more weightage because it's power 4. So the weights that are given to the extreme values is much higher. Otherwise, it is more or less conveying the same thing. And just like the way we have handled skewness by standardizing it, even the coefficient of kurtosis is handled by standardizing it only, where I divide it by sigma to the power 4. And as we have already discussed, standardization will help me in terms of comparing two random variables. And anytime we are multiplying the random variable with a constant, I don't see any kind of change in the value of the kurtosis. And as a representation, if I say that this is the typical normal value, if the kurtosis is much higher, what I generally see is the graph looks more like this. The tails are going to be much heavier. And if the kurtosis is going to be much lower, then we could typically see that the tail is going to be much shorter, right? So we see that especially when the kurtosis is much higher, we are seeing that the points are moving away from the mean drastically, and that's the reason we call them as fat tail. The tails are much fatter. That is what we mean by the kurtosis levels being much higher. And the same logic, if the kurtosis is much lower, the tails are much thinner. And skewness and kurtosis, both of them play a very important role in the world of risk management. And just as a general feeling, many financial assets today, they have high kurtosis values. Look at the stock returns. You will find that the kurtosis values are much higher for them. So there could be a possibility that two different security returns will have the same mean, same standard deviation, same skewness, but kurtosis could be different. then that particular security which is having a higher kurtosis will become more and more risky because of more and more extreme values getting possible, which will make them more and more riskier. And again, population kurtosis is different from the sample kurtosis. Observation minus the mean to the power 4 divided by standard deviation and then add it up, divide by 1 by n for a population kurtosis. But for a sample kurtosis, again, I'm not dividing it by 1 by n. I'll divide it as n into n plus 1 divided by n minus 1 times n minus 2 times n minus 3. This is what we are using. Again, this is the best unbiased estimate for the population kurtosis as well. So this would be the formula for my sample kurtosis, right? And another important point with respect to kurtosis is, we'll see that if the distribution is more or less normal, if it is more or less a bell shaped, which is more or less symmetric, there is an observation that the kurtosis value is equal to 3. And because it's more and more frequently used, people want to look at it like kurtosis is equal to 0. That's the reason they have designed another additional term called excess kurtosis. Excess kurtosis, which is nothing but the kurtosis value minus 3. And many software packages today, they directly compute, when they are saying kurtosis, they mean excess kurtosis but not the regular kurtosis. So what we say is, for a data which is normally distributed, which is symmetrical, the skewness is equal to 0, and kurtosis, which is measured by excess kurtosis, is typically 0. Whereas if kurtosis is very high, excess kurtosis is positive. Excess kurtosis is positive because very high minus 3 is still a positive number. In that case, we call that as leptokurtic. Whereas if kurtosis is lower, where excess kurtosis will be a negative number, in that case we are calling that kind of distribution as the platykurtic, where we are computing it with respect to the excess kurtosis and not the base kurtosis per se, right? So this is one more important point that we really need to understand. And the other aspect is co-skewness and co-kurtosis. Again, the concepts are more or less similar to covariance, right? We can generalize the concept where we are taking the higher order stuff, which will help us in some cases, right? Probably the simple way for us to understand is just like the way we have handled the covariance and correlation. We can also handle the co-skewness, wherein the way the co-skewness comes, right? Let's say I'm talking about the skewness between A, B, which comes out as the expected value of A. I take 2 times. So A minus mu of A squared times B minus mu of B divided by sigma A squared times sigma B. So this is one definition of the skewness, co-skewness. There is another co-skewness that can occur wherein I am considering A minus mu A times B minus mu B squared divided by sigma A times sigma B squared. So these are the two different co-skewness values that I get depending on, so I have to look at these two values before I do some kind of an interpretation. So I am getting these two different co-skewness values, right? Now the simple way to remember how many cross central, so these are the two cross central moments that I am getting. And simple way for me to understand how many cross central moments that I'm going to get is, look at this formula, m plus 1 minus 1 factorial divided by m factorial times n minus 1 factorial minus n. What is this m? So which order central moment you require? Skewness, third order. Kurtosis, fourth order. So m is talking about the order and n is talking about the number of random variables that are there. So if I'm talking of a and b, there are only two random variables. So look at this. If I want the co-skewness, how many different cross-central co-skewness that I'm going to get? M, which is 3 plus 2 minus 1 factorial divided by m factorial is nothing but 3 factorial, n minus 1 factorial is 1 factorial minus 2. 3 plus 2, 5 minus 1, 4 factorial, 24 divided by 3 factorial is 6 minus 2. So 4 minus 2, 2 is the co-skewnesses that I'm going to get. Similarly, if I want kurtosis, co-kurtosis between two variables, then if you look at A, B, 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 1, A, and then B, then I'll also get A, B, B. Now the formula also, let's take it, 4 plus 2 minus 1, 5 factorial, 120 divided by 4 factorial is 24, n minus 1 is 1, minus n is 2, 5 minus 2, 3 are there. So I am getting three different co-kurtosis values. Similarly, I am getting two different co-skewness kind of values. So I can very well get into the computations of the co-skewness as well as the co-kurtosises, how many I'm going to get for each set of variables. But here what is very much important is, though they really play a very important role in risk management, it's not that easy to compute them. Because if the number of variables n is going higher, which is what happens in case of a portfolio, what we could see is the number of the moment that I'm computing goes abnormally out of shape. And that's the reason we generally don't involve into the computation of co-skewness and co-kurtosises very heavily. Right? So that's one thing that we really need to understand. There is a concept of co-skewness, co-kurtosis, which can really be impacting the relationships between the variables. But what we will end up with is the computations being too many. And especially when I talk about the risk models, where we see that the sigmas change with time, the volatility changes with time, the correlation also changes with time, where different kinds of behaviors are possible. In this case, rather than looking at co-skewness and co-kurtosises, we use the kind of models called copula models. So they are very heavily used to really understand and describe the kind of a complex relationship between the variables, which goes much beyond the concept of covariances. And that's the reason in the world of risk management, we use copula based understanding of the relationships rather than simply going with the covariances and correlations. Right? So that's the reason we are going much beyond the co-skewness and co-kurtosises using the copulas, but in a very easily tractable kind of a framework. And so that's the reason we have to be very comfortable in differentiating these models. So they are trying to, copula based models are very much trying to understand and address the higher order cross order movements rather than simply limiting to co-skewness and co-kurtosis, right? And the final aspect of this particular session is what is this blue estimator? Blue is basic, or when we are talking about blue, it is the best linear unbiased estimator. So the words are very much important for us. So first thing is any estimator using a sample for any population parameter, one, it should be unbiased, right? And what do we mean by unbiased? The expected value should be equivalent to the population parameter. So if I am trying to compute the X bar using the sample, it means that the expected value of the X bar should be equal to the mu. So that is what we make the parameter or the estimator to be more and more unbiased. Now there could be many number of unbiased estimators for a particular parameter. So in that case, what is the best way for me to identify which is much better? It has to be more and more consistent. Just by changing the observation or the values, it should not happen that my parameter value is varying quite drastically. So it should be more and more consistent, which means the variability in the value should be much lower. So that is what will make my estimator more and more reliable and more useful. And that is what will be the choice of the estimator. And this is very much possible if the estimator is more and more linear in nature. And that is the reason that particular estimator which we use for estimating the parameters of a distribution, we typically call as the blue estimators, where we are looking at the linear as well as unbiased nature built into them. So these are the various things we really need to be familiar with respect to the statistics. We talked about the averages, the variance, standard deviation, the expectations. Then we talked about covariance, correlation, skewness, kurtosis, higher order movements, application of correlation in portfolio variance, in hedging, and co-skewness, co-kurtosis, and finally we understood what do we mean by the blue estimators. All right. So thanks a lot for listening to this session. Thank you very much.